So, a very good evening and a warm welcome to this interactive session with the instructor in the course Foundations of Wavelets and Multirate Signal Processing. I'm Vikram Gadre, and I'm going to be here to answer your questions and respond to whatever you wish to discuss in this session. Right? So, first and foremost, can we see how many participants are viewing this session? Perhaps, is there a way to see how many participants are viewing this session? Okay, so concurrent two viewers are. So the two viewers who are here, could you introduce, maybe you can introduce yourself in the chat, and then you can put your questions in the chat. I'm also taking questions, if there are any, from the from the sheet that you've sent, Google form, which you must have filled. So among the concurrent viewers, those who are viewing this session, any questions? Okay, so I'm here. I'm happy to respond to what you wish me to discuss this evening. You can put your inputs into the chat. I'll be happy to respond. So once again, I mean, for the viewers who are on this session, please feel free. I don't see any questions that have been posed in the Google form, in the form that was circulated before. But if there are any questions which you would like to pose now, you're very welcome. Please come forward with your questions or anything that you would like to discuss. This is a live session in the course Foundations of Wavelets and Multirate Signal Processing. It's a 4-week course. So this is an opportunity for you to discuss your questions, if you have any comments, if you have any concerns, whatever it is. It's an opportunity for you to interact live with the instructor. Please come forward. You can post your questions in the chat. In fact, why don't you start by introducing yourself? Those who are here, why don't you introduce yourselves? So at least the viewers who are here in the session, it'd be nice if you can introduce yourself so that once you break the ice, as they say, it'll be easier for you to ask questions or to share your thoughts and so on. Good, at least we have an increasing number of viewers. So I would recommend the viewers introduce themselves so that we can get to know one another, and thereby it will be good for you to feel more comfortable to share your thoughts, ask questions, make comments, and whatever it is. Very good. So I'm very happy to see that Krishna Chand Avatar has responded in the chat box, the chat forum. It says, hello, Professor. Thanks for your lectures. I'm Krishna, a PhD student from Department of Aerospace, and very hello. Very good. What would you recommend as the next step after the course? You must think of how wavelets might be how you might be interested in implementing wavelets in your application. So this course is meant to give you a feel of what wavelets is about. And, it's wavelets has wide applicability. In fact, even in fluid mechanics, for example, I'm aware that wavelet-based principles are used for the analysis of turbulence. So maybe, as a student of aerospace engineering, it may be good to see how maybe in subjects which are relevant to aerospace engineering, for example, fluid mechanics or fluid dynamics and so on, in the analysis of turbulence, how you can employ wavelets. Since you're a PhD student, maybe you can share, how you might find some uses of wavelets. Okay, on the mechanics of structures. So Krishnachand Alsar says that his research is on the mechanics of structures. For example, I believe that you use finite element methods. Is that right, in structure analysis? If that is the case, then finite element methods also benefit from use of wavelets. You may want to look it up. You can go to Google, you can go to IEEE Explore, and you can use these keywords, wavelets and finite element methods, or finite difference approaches, and so on. So wavelets could be useful in, I'm just assuming, I'm not an expert on the mechanics of structures, but I dare say you might find the finite element method useful in structures. Am I right, Krishnachand Avatar? Oh, very good. That's very nice. I'm so very happy to see that you did a project on wavelet analysis in a course on fluid mechanics. Yes, so in fact, in the analysis of turbulence, wavelets have been found to offer many advantages. So you look at that possibility of using in analysis, in using wavelets for analysis of turbulence phenomena in fluids. I really wish you could speak live. Unfortunately, we don't have that provision in this channel. I must also thank you for being the PMRF TA for this course. So so it's very nice. I'm very happy to, to note that you were the PMRF TA. What was your experience? Maybe you can share your experience as a PMRF TA. Yes, absolutely. Wavelets can be used to analyze both spatial and temporal waves. In fact, if you are doing analysis in more than one dimension, then you can also use what are called non-separable wavelet methods. In fact, it may offer you also some possibilities for research, the use of non-separable wavelets in, in fluid analysis, fluid dynamics. In the Institute of Science, Bangalore, I would recommend you must also talk to Professor Chandrasekhar Seelamantula in the Department of Electrical Engineering. And you can discuss the possibilities of using non-separable wavelet-based approaches in fluid dynamics, if that helps your PhD. Can the other viewers also introduce themselves? So I'm very happy to see that Krishna Chand Avatar. Very good. So Krishna Chand Avatar says he got to learn about wavelet analysis from a signal processing perspective. Yes, of course. And it helped revise these concepts. In fact, wavelets is a subject which brings together people from many disciplines. Of course, the discipline of signal processing, that's where a lot of the work has been done. But also, there's a strong section of mathematicians, people working in function analysis, and maybe, in some of these spaces, Banach spaces, Hilbert spaces. So they would look at the subject of wavelets. And in the applied disciplines, oh, very good. I'm so happy. I'm glad that you gave some MATLAB and Python-based tutorials to add to understanding for the course participants. I really appreciate these efforts that you've made. In fact, you have encouraged me, we must seriously think now in the current age, we must seriously think of how we can build a course which brings together wavelets and machine learning or machine learning, deep learning, neural networks. There are already lots of pointers to that. And I'm thinking of creating a course which brings together wavelets, multi-resolution signal processing, machine learning, deep learning, neural networks. That's the current era of the huge success of machine learning and deep learning. There are many ways in which wavelets actually offer advantages in machine learning, deep learning to bring in economy and explainability. Some of my students have been looking at that. Yeah, it is harmonic analysis. See, I'm not sure if wavelet analysis can be called harmonic analysis. It's definitely it would definitely qualify as functional analysis, or analysis with orthogonal functions, yes. I'm not sure if you can call it harmonic analysis. Well, in a way, I mean, I've seen number of references which talk about the connects between wavelets and harmonic analysis. See, in a way, I mean, when you look at different subbands in a wavelet analysis, you're looking at different possible harmonics. I mean, only thing is that the typical, or you may say the quintessential wavelet analysis does what is called logarithmic analysis on the frequency axis. It's not quite, so you're not quite dividing the. Oh, very good. So you've also been reading functional analysis. So it forms a part of your PhD research. How long have you been in your PhD program now? And have you kind of frozen the broad theme of your PhD? Not the specific problems, but the broad theme. Okay, wonderful. You're in your fourth year. So you might have kind of converged on a broad theme. Oh, that's very nice. It's on magnetism and mechanics of elastic slender structures. I'm sure, do you use any form of finite element analysis or, discretized analysis in the analysis of these structures? Wavelets are a very powerful basis for finite element analysis also. In fact, I had a colleague who retired, unfortunately, who is no more now, who would work on or who had some interest in employing wavelets in finite element analysis. He was a world-renowned authority on finite element analysis, and he found that there are very interesting applications of wavelet-based methods in finite element analysis. So you are using advanced mathematical tools for analysis to investigate bifurcations and stability. That's very interesting. So you see, the advantage of using wavelets in such problems is that they allow you to do two things. One is they allow you to see phenomena at different scales. A phenomena which spreads over a broad range of the medium or whatever it is, and also localized phenomena. So you can see them simultaneously. metaphorically, we say wavelets allow you to see both the wood and the trees. So it shows you the whole forest. It also shows you individual trees. That's a way of looking at both coarse and fine analysis. So the ability to analyze both coarse and fine is a strong advantage of using wavelets. Now, I'm sure there are such problems in bifurcations and stability analysis that you're doing, which require you to look at both coarse phenomena, coarse, the phenomenon which spreads over a wide range of the medium, and also finer phenomena which are localized to some parts of the medium or whatever it is. So there you might find wavelets very useful. In fact, I dare say that you might find some benefits in using non-separable wavelet analysis. It's inherently two-dimensional wavelet analysis, which of course is too advanced for this course on foundations of wavelets, but it's not, once you have an idea of what wavelets are, then you could start building a background on non-separable approaches as well, because it might offer some potential for novel. Okay. So highlight about the computational. Good. Now, the wavelet approach, in fact, the way you implement wavelets, so let's take, let's try and use the chat, where is the whiteboard here? We need a tablet, right? Yeah. Yes. Now we need to share it. Yeah. So Krishna Chandauda, can you see the tablet I'm using here? Now, so are you able to see the tablet, Krishna Chand? So now, you see, the way you implement wavelets is by using what is called a two-band. So use a use a two-band filter bank. So you feed a stream of what you may call samples or a sequence which comes. Now, you may think of this, let's take a one-dimensional situation first. So you implement the wavelet transform by first assuming that you know the discrete representation of an underlying continuous signal. So let's take an example. Suppose you have a continuous signal. Okay, let's say it's a function of time. Now, one simple way to discretize it is to divide this into very small intervals. And in each interval, represent the signal. Let's call it xt. So we represent xt by its average value on very small intervals. So in each of these intervals, you You find the average. So how do you find the average? You integrate the function on that interval and you divide by the size of the interval and you get an average. So in each interval, you would use one constant. That's the average to represent the function. And if your intervals are small enough, then it is a reasonable representation of the function. So now, what do? You thus get a sequence. So you get a sequence of averages over small intervals. And you feed this to two filters. A low-pass filter and a high-pass filter. Of course, these are discrete filters. And then there's a downsampling by 2. That gives you the discrete wavelet transform. Or DWT, as it is abbreviated. And of course, the inverse is also a kind of transpose operation. But I mean, when you want to calculate the wavelet transform, you're essentially doing two filtering operations followed by two downsampling operations. Yeah. So you can see how the computation is growing, or rather, how the computation is progressing. So suppose, for example, you have a sequence of length n. Let's try and put the sequence length here. Let's say the sequence length is n here. Then, roughly speaking, you're doing some computation and you get length n by 2 sequences here, roughly. Okay. And you iterate this structure on the low pass branch every time. So as you can see, typically if you have if you have a sequence of length n, the order of or the computational complexity is of order, it's calculated. Oh, sorry. Okay. Is of order of computational complexity is roughly n plus n by 2 and so on, n by 4 and so on. You can keep doing this, right? So you can see it's converging to order n, essentially, and into n, if you go keep doing this. So the computational complexity is roughly of the order of the number of samples, because each time you're downsampling. So in that sense, there's a computationally efficient approach to implementing the discrete wavelet transform. The inverse discrete wavelet transform also has a similar kind of computational complexity. So for a discrete wavelet transform, the computational complexity is the order of the number of sample points, the data size. And of course, you can say it's a multiple of that data size, but it would be typically a small multiple. In fact, the multiple will also depend upon the size of the filter that you're using. Now let's take the example of the Haar wavelet. In the Haar discrete wavelet transform, the low pass filter essentially averages the current and the pass sample. And the high pass filter computes the difference between them. So when you average, you're in fact doing some kind of a low pass operation. And when you compute a difference, you're doing effectively what is like a high pass operation. So yeah, let me now, you have a question. Since we also traverse all dilation and translation parameters along the signal sample, what would be the computational costs? See, the dilations, every time you do this low pass and high pass pair of operations and the down sample, you have taken care of the dilation. And translation, you see, the translation is happening because you're moving the filter kernel along the sequence. That takes care of the translations. So, when you're doing in the discrete filtering operation, the process of moving the impulse response or the filter kernel, as you call it, along the data sequence essentially takes care of translations. And the fact that you're downsampling and then iterating this on the low pass branch every time takes care of dilations. So we have included that in our process of implementation. Is that addressing your question? Now, depending on which wavelet you're using, you would have different low pass and high pass filters. And very often, many wavelets might perform similarly, but there could be minor differences, between different wavelets. But there are subtle nuances which determine, if you take, for example, the Dobeschi family of wavelets, then the higher you go in the order of the Dobeschi wavelet, the higher the degree of the polynomial that you're annihilating on the high pass branch. Yeah, in continuous signals, see, the implementation of the wavelet transform in continuous signals proceeds in two ways. One is that you sample the continuous signal, or you could, whatever your operations you want to do in the continuous wavelet analysis, you discretize those operations very finely. That is what you would try to do in continuous signals. But if you tell me a more specific context where you might find wavelets useful in your work, we can help sort out some of your questions. So while Krishnachand poses his questions, is there any other participant who wishes to pose questions or ask anything? Okay. So one application in your work could be in spatially varying signal due to the formation of localized instabilities. That's very interesting. So in fact, the moment I hear the word localized, I think that's a very good reason to be using wavelets. Because, in fact, wavelets have a lot of merits in the analysis of singularities. So the analysis of singularities. In fact, there are several references which talk about how wavelets is a very powerful tool for the analysis of singularities. When you refer to the formation of localized instabilities, I imagine that you might have some reason to believe if you look at if there is some particular function that you're tracking as a function of space, it's a spatially varying signal. You're trying to track some signal as a function of space. I dare say there must be some singularities which indicate instabilities in the signal. So if there are singularities, there's a lot of literature on wavelets as a powerful tool to handle singularities. Singularities could be singularities in the function, which means discontinuities in the function, or they could be singularities in the derivatives or higher order derivatives, So those are handled very well with wavelets. Wavelets is a very powerful tool to handle singularities. Also, you were asking about non-separable approaches. There are several. In fact, you just all that you need to do is to go to IEEE Explore, which is I think you may be using IEEE Explore in your library resources, and you could look up with the keywords. I'll give you some examples of keywords. You could say, shearlets, contourlets, or curvelets. And you could look for, and you can say singularity. These would be two-dimensional, multi-dimensional singularity. So then, there might be some literature. I'm just giving you a way to search, and you might find some work on this. So, deformations of thin structures. Now, when you're talking about deformations, there would definitely be, so shearlets, I dare say that shearlets or contourlets or curvelets, which are inherently two-dimensional multi-resolution analysis techniques, might find applications in these deformations, because these deformations are not going to be necessarily aligned along the horizontal and vertical. So you would need to allow for non-separable analysis, two-dimensional analysis. So I would recommend you look up IEEE Explore and use these keywords, these keywords In fact, you can even give the keywords as deformation and then look at non-separable approaches, and so non-separable is a very broad word, but you could look at these keywords: shearlet, contourlet. If I had the resources here, I would have probably done an IEEE explore right here and shown you, but you can probably do it on your on some local PC there, a local laptop there. I think you have a very rich area of research. I'm sure that you'll be able to find some very interesting applications of non-separable approaches that might give you a good direction for your PhD. I definitely recommend you speak to Professor Chandrasekhar Seeramantula, writing it here. The Department of Electrical Engineering. Yes. Have you already contacted him before? Oh, if you have not, then I would certainly recommend that you would talk to him. Seek an appointment with him and talk to him and give him my reference if required. Would you like me to explain anything further, Krishna Chand? In fact, I'll put down my email address. You'll also find it on the web page, but I'll just put down my email address and I'll be very happy to discuss more with you. We can also have a separate video call. I'd love to interact with you since you're so into my email. And we can also, you can write an email to me and then I can correspond with you individually. And then, please let your name be there in the reference of this discussion. And we can also connect on a video call if you would like to know more. And you might find some very interesting directions using wavelets in your work. It's very nice. You hold a lot of interest in various areas, spanning control theory, mechanics, applied mathematics, signal image processing. Very good. Very nice. And Wavelets has a lot of applications in many of these. Anything else that you would like to discuss, Krishna Chand? Or should we close the session? I don't see anybody else participating in the session. And once again, I would like to appreciate your contribution to this course by being a PMRFTA. I think that's a very valuable resource that we have to run such a course. And congratulations on being selected for the Prime Minister's Research Fellowship. Very creditable indeed. So should we close the session then, Krishna Chand? Okay, we can close the session, I guess. Nobody else who's participating. But I must also appreciate your participation, Krishnathan. That has made the whole session worthwhile. And I'm sure many silent observers have gained a great deal from your participation in this session. Must all appreciate Krishnachand Avatar for making this session very valuable indeed. Yes, we can close the session then, because we don't have. Thank you. So we will once again appreciate Krishnachand Avatar for making this session very valuable, very interactive, and for bringing up many important questions. And we hope that other participants also come up with questions and comments. And we'll now close this session.